Hello everyone. In this video, I will tell you about the anomalous properties of carbon. Okay, carbon is the first element of the group 14 elements. Now we have also seen that many of the other in other groups, every time the first element of each group is very different from the other members. Okay, similarly over here also, carbon is quite different from other elements of its group. Okay, so we will discuss about the anomalous properties of carbon now. Okay, in fact, the properties of carbon is so unique that we have an entire branch of chemistry, that is the organic chemistry, on just the compounds of carbon. Okay, so we would just see that what is the reason for such a large number of formation of carbon compounds. Okay, so the topic is anomalous behavior of carbon. Okay, okay, yeah. So the reason for this behavior of carbon, okay, carbon behaves indifferently from other elements of its groups because of its small size. Okay, this is the first factor. The second factor is that it has high electronegativity value. Okay, so basically carbon has very small size, it has high electronegativity, it has high ionization energy, okay, and it has unavailability of d orbital. Okay, so only p orbitals, take the carbon has only take p orbitals and there are no free d orbitals. Okay, now due to this reason, carbon cannot extend its covalency. That you very well know up till now, that carbon cannot extend its covalency. Okay, now the another important property, and in fact the very important property of carbon is this. Let me write it another color. Is this: carbon has a unique ability to form, okay, p-pi bonds. P-pi bonds with itself, okay, and with other atoms of small size and high electronegativity. Okay, now carbon has a very unique property, okay, to form p-pi bonds with itself and other atoms of small size and high electronegativity. Now you very well know some common compounds of carbon. Okay, like you very well know that carbon forms single bond, carbon also forms double bond, carbon also forms triple bond, and carbon forms bond with oxygen, carbon forms bond with nitrogen, etc. Carbon also forms bond with sulfur, and there are so many examples. The important feature is this, that carbon has a very unique property to form these bonds. Most of the other elements do not have the property of forming bonds with itself to a very high extent. Carbon has a very high tendency to form bond with itself and with other atoms of which have a small size and high electronegativity. Due to this reason, okay, there are so many compounds of carbon. To this reason, we have so many compounds of carbon. Okay, this is the main reason, that carbon forms bond with itself and with other elements. Okay, and there is one more. You can also say there can be one more reason, is that carbon has a property of catenation. What is catenation? We will just see in a few minutes. Okay. Now, what happens is that now you might be wondering that why does carbon does not form bond with the other elements? Why only small elements? Okay. The reason is that carbon does not have tendency to form stable bonds with heavier elements because of, can you guess? Because of, the first point is, the first reason is they have large atomic orbitals. Okay, the heavier elements have large atomic orbitals, and so there is diffused overlapping. Okay. Okay, this means that suppose here is the orbital of carbon, okay, and here is the orbital of a heavier element. Okay, so the overlapping region is this, okay, which is quite diffused. Obviously you can see that if this is carbon and this is say lead, okay, then the atomic orbital of lead would be quite large, but that of carbon would be very small. So the overlapping, the intermixing part, this intermixing part would be quite less. But in case of smaller elements, like this is carbon and say this is oxygen, so the mixing part in this case, because of the similar size, the mixing part which is over here, okay, is quite good. Therefore there is sufficient overlapping to form very strong bonds. Okay, so this is the reason that we have this, we do not find heavier carbon forming bonds with heavier elements. Okay, now another property which we would see of carbon is that of catenation. Okay, what is catenation? Okay, catenation is the tendency of carbon to form bond with itself and thus forming chains and rings. Okay, so it is the tendency to link with one another through covalent bonds. Okay, forming chains and rings. Okay, now this is another property of carbon which is observed, which is quite important, that carbon, you very well know that compounds of this sort, okay, you can easily find compounds, long carbon compounds, okay, and similarly you can also find compounds of this sort. That carbon is linked with carbon, okay, it has a very high tendency of linking with itself, and this property is called catenation. Okay, now the reason for this property is, okay, this, and the reason is, what is the reason? The reason is carbon-carbon bond is very strong. Okay, that carbon-carbon bond is very strong. Okay, therefore carbon easily forms bond with carbon, stable bond with carbon. Okay, now due to this property of catenation, okay, and pp bond formation, carbon has shows many allotropic forms. Many allotropic forms means many existence of carbon. Many forms of existence of carbon is observed in nature. Okay, so due to catenation and p-pi bond formation, okay, carbon is able to show allotropic forms. Okay, carbon has a tendency to show allotropic forms. Now we would see some very natural, common, well-known allotropes of carbon. Okay, the first allotrope is, which you would see, is the precious diamond. Okay, the diamond. Okay, so diamond. Now, diamond. What is the structure of diamond? Okay, the structure of diamond is a crystalline lattice. Diamond is a crystalline lattice. Okay, diamond has a crystalline lattice structure. Okay, so, and what is another important feature? Next important feature is that each carbon atom is sp3 hybridized. Okay, so each carbon atom in diamond is sp3 hybridized. Okay, and by meaning sp3 hybridized, that means we mean that it is, I mean, each carbon, okay, is linked with four other carbon atoms. Okay, each atom is linked with four other carbon atoms. Okay, now this linking is in tetrahedral manner. Okay, this linkage is in tetrahedral manner. That means that there is a carbon over here, there is a carbon over here, there is carbon here. Okay, and this is what 109 degree 5 minutes. Okay, this is the linking. This is how carbons are linked. Okay, now what is the CCC, carbon-carbon bond length? Okay, so we want to know that what is this bond length. The carbon-carbon bond length in case of diamond is 154 picometer. Okay, this is the carbon-carbon bond length in case of diamond. Okay, now we would see the next allotropic form of carbon, that is again the lead in the pencil which you use, that is the graphite. Okay, now graphite has layered structure. Graphite has layered structure. Okay, this means that there are layers of graphite actually. Okay, like, let me draw the structure for you. Okay, the graphite structure is something like this. Okay, consider this as one layer. Okay, this is a layer of graphite, and then there is some linkages present over here. Okay, and then there is the next layer. Okay, so this is how is the structure of graphite. That there is one layer over here, then there are some linkages, okay, and then there is next layer at the bottom of the layer, or of the top layer. Okay, so this is the structure of graphite. Now, the next point is that each layer of graphite, okay, is held by van der Waals force of attraction. Okay, each layer, that is this all is van der Waals force of attraction. Okay, all these, they are held by van der Waals force of attraction. Okay, now the distance between this, okay, the distance between these two layers, okay, this distance is how much? This distance is 340 picometer. Okay, this distance is 340 picometer, but this distance is, this carbon-carbon bond length is how much? This distance is 141.5 picometer. Okay, so you can very well see that this distance is quite larger than this distance. Okay, that is why we can say it has a layered structure. Okay, now each layer, as you can very well see in this diagram also, that each layer is comprised of hexagonal rings. Okay, each layer is comprised of these such similar hexagonal rings. Okay, and each carbon is sp2 hybridized. Okay, each carbon, all these carbons are sp2 hybridized. That means that they have, this means that this carbon forms bond with these three carbons, and the one electron left over here, this is delocalized in the whole sheet for every carbon. Okay, the electron left over here is delocalized in the sheet. Now by sp2 hybridization we mean that it has 3 sigma bonds. Okay, there are 3 sigma bonds. Okay, and fourth electron is delocalized in the whole sheet. Okay, by delocalized means that fourth electron is free to move in the throughout the sheet. Okay, now if electron would be free to move, then what will happen? It would easily conduct electricity. Okay, because electrons are the chief source of conducting electricity. Therefore, we would say that graphite conducts electricity along the sheet. Okay, graphite conducts electricity along the sheets. Okay, and the next point is, now since the bonding between this 340 is 340 picometer between the two layers, graphite is very slippery and can easily be cleaved from the layers. Okay, so we would write that graphite is soft and slippery and can be easily cleaved between the layers. Cleaved means distorted and removed. Basically, the layers can be separated. Graphite can be broken easily. Okay, through the layers. Okay, because the bonding between the layers is 340 picometer. Okay, the next we will move on to the next allotrope of carbon, that is the fluorines. Okay, so graphite and diamond exist in natural form. Okay, but fluorine, they are man-made compounds, you can say. Okay, so they are formed okay, by heating graphite, okay, or they are formed by heating graphite, okay, in elliptical arc in presence of inert gases like helium, argon, anything. Okay, so fluorines are formed by heating graphite in elliptical arc in presence of inert gases. Okay, now okay, so this is how fluorine is formed. Now it is the, you can say, the only pure form of carbon. Okay, it is only pure form of carbon. Okay, so what do I mean by this word only pure form? Okay, so by this I mean that there are no dangling bonds. Okay, by this I mean that it has smooth structure with no dangling bonds. Okay, so what do we mean by dangling bonds? Okay, now consider this. Suppose that you have taken diamond. Okay, so diamond, how the structure would be? The structure would be something like this. Okay, this carbon, it would be linked to other carbon atoms. Similarly, this carbon, it would be linked to other carbon atoms. But obviously, you must have understood that at these edges, okay, these carbon atoms would not be linked to the other carbon atoms. Okay, I hope you are getting this point. So these bonds would be left dangling. Okay, this is what we mean by dangling bonds. Okay, similarly in case of graphite also, that if we draw the structure at this edge, at this corner, suppose this is the last, graphite ends after this, so this carbon would be left. Okay, there would be a dangling bonds because this carbon is only attached to the other two carbons. Excuse me. This carbon would be attached to the other two carbons, and so it would be dangling. But in case of fluorine, what happens is that fluorine is attached with only carbon and the structure is complete entirely. There are no dangling bonds. This is the unique feature of fluorine. Okay, that the structure is complete. Now you must have seen somewhere, you can look up on the internet, the structure of Buckminster fluorine. Okay, now it has actually, the fluorines have cage-like molecules. Okay, so there are no dangling bond means that fluorines have cage-like molecules. Okay, like one of the example is carbon 60. Okay, C60. C60 is also called Buckminster fluorine. Okay, it has shape like soccer ball. You must have seen football or soccer ball. That is the exact shape of C60. Okay, enlarged. Okay, now you see that there are no dangling bonds. You can consider every hexagon and pentagon as the corners of hexagon and pentagon as carbon. So you can see that it is complete in itself. There is no dangling bonds and no edges. Okay, now it is also called, let me write that, it is called Buckminster. It is called Buckminster fluorine. Okay, it has 26 6-membered ring and 12 5-membered ring. Okay, so Buckminster fluorine has 26 6-membered ring and 12 5-membered rings. Okay, Buckminster fluorine also has a unique feature that 6-membered rings are linked to 6 or 5-membered rings. Okay, but 5-membered rings are only linked to 6-membered rings. Okay, this means that no 2 5-membered rings are linked with each other. Okay, this is another important feature of Buckminster fluorine. Now that what is the hybridization of carbon? Okay, carbon is sp2 hybridized. Carbon is sp2 hybridized. Okay, and it has 3 sigma bonds and 4th electron is again delocalized. It has since it is sp2 hybridized, it has 3 sigma bonds. Okay, and the 4th electron is delocalized in the molecule. Okay, now due to this delocalization in the molecule, fluorines have aromatic character. Fluorines have aromatic character. This is the reason of fluorine showing aromatic character, because the electrons are delocalized in the molecule. Okay, now let's also see some facts regarding the allotropes of carbon. Okay, So let's see some facts regarding allotropes of carbon. Okay, the first fact which I would write down is graphite is thermodynamically more stable. Okay, graphite is thermodynamically more stable form of carbon. Okay, graphite forms, reacts with F2 fluorine, okay, forming, it forms intercalation compounds. Okay, basically it is just a fact which you need to remember. The compounds are like this. Okay, so if you would be asked, you would be only asked that graphite reacts with F2 to form what? So graphite reacts with F2 to form intercalation compound, that is CFN. Okay, the next fact is that diamond is unaffected by concentrated acid or base. Diamond remains unaffected when you put it in, try to react it with concentrated acid or base, while graphite reacts with metallic acid graphite reacts with metallic acids, okay, to form, graphite reacts with concentrated acids to form, benzene, hexacarboxylic acid. Okay, so graphite reacts with conc acids. Okay, graphite reacts with conc acids to form benzene carboxylic acid. Okay, the structure of benzene carboxylic acid is this. Okay, this acid is also called magnetic acid. Okay, so graphite reacts with concentrated acids like HNO3 to form this. Okay, but diamond is unreactive towards concentrated acids. Okay, the next fact is that the next fact is not regarding the allotropes of carbon, but a general fact which I would like to tell you, that germanium liquid, okay, it expands on heating. Okay, this is just a fact which I would like to tell you, that you might be asked sometime, that germanium liquid expands on heating. Now this property this property is similar to gallium also and bismuth also. Okay, this property is similar to gallium and bismuth. Basically what I mean is that germanium, gallium and bismuth, all these liquids expand on heating. I'm very sorry, these expand on solidification. Okay, germanium liquid, gallium and bismuth, all of these expand on solidification. Okay, although they must have contacted, you must know that liquid when solidified contracts, but these three liquids expand on solidification. Okay, so in this video what did we see? In this video we saw that first of all we saw the anomalous behavior. Why does carbon shows anomalous behavior? Because of its small size, high electronegativity value, okay, high electronegativity value and high IE and unavailability of d orbital and unique ability to form p-pi bonds with itself. Okay, these were the reasons. Due to this we observed so many compounds. We also saw the reason why carbon does not form p-pi bonds with heavier elements. We saw the property of catenation and its reason. We then moved on to the allotropes of carbon. We first saw diamond, okay, its structure, the hybridization. We saw graphite, its structure, the hybridization of carbon and the some few properties. Then we saw fluorine and its structure. Okay, you must also, I would recommend you to look at the structure of Buckminster fluorine on the website. Okay, you must know the figure of it. Okay, now next we saw some facts regarding them. Okay, so that's all for this video. In the next video I would be telling you about the oxides of carbon. Okay, thank you.